Welcome back to Codex. Today we have Oscar Mickelin from Princeton University. Dr. Mickelin is an expert in mathematical data science. Today he'll tell us about fast Fourier-Bessel expansions. Take it away, Oscar.
Thank you so much. I should say before I start, I'll probably get tunnel vision and not necessarily see if there's a question in the chat, so please just shout it out. That's better. Okay. Thank you very much for the invitation. So in honor of the name of the seminar, I'm going to talk about some code. So that's going to be this fast algorithm that does some expansion into this very particular basis. That's called the Fourier-Bessel basis. So this basis has something to do with harmonic analysis, so it will also fit that theme of the talk. So what we're going to do is we're going to go through all the details of this algorithm. And sorry, let me just, there we go. Yeah, we'll go through all the details, and then towards the end, we'll launch into an application if there's time. And everything that I will talk about is joint work with Nick Marshall, who's now at Oregon State, and my postdoc advisor, Amit, who's here at Princeton. Okay, and if we do make it to the application, there's going to be one more co-author there as well. Okay, so what are we going to do? Well, we're going to think a lot about images, or at least image-valued data. So assume that you've been given, an array with pixels of an image. Often what you want to do is you want to expand this image into some kind of suitable basis so that you can do, computations with this basis. The particular basis that we are going to be concerned with is the one that I present here. So it's double indexed. There's an n and a k. And then for each nk, we have a function psi. Okay, and it's given in polar coordinates in this way. First, there's a normalization constant. And then we have a radial function, which is a Bessel function. So Jn is the nth Bessel function of the first kind. And then lambda nk is the kth root of Jn. And then in the angular part, we have Fourier modes. So that's why it's called Fourier-Bessel. Okay, so as you probably know, these guys, they are eigenfunctions of the Dirichlet Laplacian on the unit disk. And I've tried to plot some of them here. You might have to break your neck a little bit, but I have, let's see, I have 10 different eigenfunctions here. So this is psi nk, where the first variable that's n, second is k, and the third is lambda nk. And I've arranged them in increasing lambda here. Okay, so this is just illustrates what the basis functions themselves look like, but what do we want to do with this? Well, like I said, we want to expand images into this basis. So as a small little test, we're going to expand this ground truth here. So it might not be really clear what this image is, but it's related to the application that I mentioned that we might talk about later. So this is a biological molecule, but it just looks like cotton candy or something. Okay, so we take this image and I expand it into this basis using a varying number of basis coefficients here. So here I have very few, and then have a little higher number of basis coefficients, and then higher and higher. And if we keep going, we'll end up with something that looks very much like this. Okay, so that's going to be the object of the talk. We want to be able to do expansions like this. And in fact, these images were generated using the fast algorithm that I'm going to present. Okay, so that's what we're trying to do, but then why are we trying to do it? Well, like I mentioned, it's probably pretty okay that we want to expand the images in some kind of basis, just so we can do computations with it. But why this particular choice? Well, it turns out it has quite a few nice properties. So I just listed 4 of them here that I happen to care about, but I'm sure we can come up with other ones. So first of all, these basis functions are orthonormal, which makes it nice. Secondly, this lambda parameter is associated with a physical frequency. So that means that if I go back, if we arrange all these functions in order of increasing lambda nk, so not increasing n, increasing k, but increasing value of lambda nk, then we get a notion of being able to do low-pass filtering. And that's what I did here. Okay, so this bottom figure, it has the fewest number of coefficients and also just the lowest ones, the lowest lambda nk. And then we can increase them. Okay. So that's 2 of these nice properties, but then there are more. One that's going to be important for our application later is that these basis functions are steerable, meaning that it's very easy to rotate images once you've expanded them. So I tried to illustrate it here. So this is Fourier. And what I did was I took this image and expanded it into basis. And then I applied a diagonal operator on these coefficients, after which I re-expanded it to this Cartesian grid, and I get back a rotated version of Fourier here. Okay, so I'm not using Photoshop. I'm not taking this and just rotating it, because that would be lossy, but because we have to do some interpolation. But now instead we have a lossless rotation once we've expanded. Okay, so that's number 3. And then for number 4, this will be crucial for the application later, but it might seem a little bit random now. But it turns out if you really, really want to take an image and convolve it with a radial function, then you can actually do that efficiently in the spaces, because this turns out to be a diagonal operator. Okay, I have a table here just comparing this basis with some other ones that you might be caring about. So we will look at this last row here. That's the Fourier-Bessel row. And then the first column is whether or not this is orthonormal, if it's continuously steerable, if you have this property about radial convolutions, and then lastly, if there is a fast algorithm that expands images into the spaces. Okay, so basically the next half hour will be just about this bottom right green check mark right here. Okay. Good, so hopefully it's clear now what we're going to do and why we want to do it, but I just want to say a few words about this application that we'll return to later. So my postdoc advisors group here at Princeton looks a lot at cryo-electron microscopy. So that's a tool that uses a lot of image processing techniques. So typically what you end up with are images of biological molecules. And if you have clean images, they look something like this. It looks like a mushroom. But often what you get from experimental data sets is not like a clean mushroom. You get something that looks more like this. So there's so much noise that you can barely see that there's a signal there at all. So what can you do with this noisy thing? Well, hopefully you would want to be able to denoise it. Okay, so that's the last column here. And this last column is something we achieved using the techniques of this talk that we'll get to later. So hopefully you can see that it's not perfect. There are some artifacts around it, but this column is much closer to this column than this noisy thing. Okay, so how do we actually get there? Well, it turns out we have to do some rotation invariant PCA and covariance estimation. So in case anyone is interested in PCA under group actions, we'll talk about this later. But I just have this one slide here. So the top column is a PCA on one of these data sets, but on the clean ground truth data set right here. And the middle row is PCA that we achieved using our techniques on the noisy images. And just, you can compare this to the first row and see that they're pretty similar. And then as a contrast, on the bottom row is an older technique in the literature, in the cryo-EM literature, that tries to do the same thing, but you can see that it is lacking a little bit in the quality. Good. So I've tried to motivate it now. So the next question that might pop up is, why is this not a very easy problem? So I'm not claiming that what I'll show you is hard, but it's at least going to be a little bit harder than what's on this slide. Because if you look at this basis function, the first observation that you make is that it's separable in a polar grid, right? So we have a radial part and an angular part. So why can't we just do a product quadrature on our image? Well, in our case, we can't do that straight away because the image that we get is actually given on a Cartesian grid like this. It's an actual image where typically you get pixels arranged in a Cartesian grid. So we can't just separate variables straight away. But then the next thing you might try is, if we have a Cartesian grid, why don't we just interpolate it onto a polar grid? So we go from here to here somehow, and then we can use a product grid. Oh, sorry, product quadrature. So you could try this if you want, but it doesn't really do what we want, because if you look at the accuracy of this interpolation, that's going to depend on the properties of the underlying image here. So if they're sampled from a smooth function, you can, you get some bounds. But we want to get accuracy guarantees that are independent of the smoothness. And in fact, we want to do it for these noisy images that are not even continuous. Okay. So what do we do then? Well, let me show you the main result that we'll go through. Okay, so there's some notation. So we're going to look at an image like this. So we're going to just enumerate the pixels by xj. Okay, we have an LYL image, and then fj are going to be the corresponding pixel values. So when we want to do these expansions into the basis, there are two operators I care about. So they're going to be B and B adjunct. So B takes a set of basis coefficients alpha and just expands those coefficients onto the grid by multiplying by the corresponding basis functions at all the grid points. Okay. And then B adjunct does the opposite. It just takes an image and computes the inner product with all these basis functions. So if we want to do this in a dense way, what would we do? Well, we would just form the matrix B. Okay, so we would take all the basis functions that we care about, put them in a matrix, and evaluate them at all the grid points in the image. So that's going to be L squared grid points. And it turns out if you want to capture all the information in the image, you should have of the order of L squared basis coefficients as well. So you'll have an L squared by L squared matrix. And if you want to compute this inner product, or sorry, this math vector product, it'll be of the order of L to the fourth. And that is too slow for us. So instead, what we want to do is come up with some clever algorithm that gives us approximations B tilde, approximation to B, B adjoint tilde, approximation to B star, that can be applied in a quicker way. And it turns out we can get away with doing it in time L squared log L, which is much less than L to the fourth. Okay, and then there's this additional complexity term here, which depends on an accuracy parameter epsilon. And epsilon is here in the accuracy guarantees. So the approximation B tilde star minus B star is less than epsilon times the normal. And same for B tilde here. So here, just one observation, you might be wondering why we have this funky norm L1 here and L infinity there and not just L2, L2. So this falls out because we'll be using some non-uniform FFTs where this is a nice norm to use. But if you're not super happy with it, I'll also have some empirical results later on that replace this by L2 and L2. Okay, so this is the result that we're going to talk about for the rest, at least of the first half of the talk. So I want to go through the construction of these operators B tilde, so the algorithm for applying them, and how we get down from L to the fourth to L squared log L in complexity. So it turns out to have a fairly straightforward basis for this. Sorry, basis not in the linear algebra sense, but like the basis of the algorithm is fairly straightforward. Because there is this analytical identity that we're going to use. So let's go through it. Assume that we have a function that's expanded in this basis. Okay, so here I is just some finite indexes because we don't have infinite coefficients. What we do then is we define a helper function beta with this formula. Okay, so we take the Fourier transform of f and we evaluate it in polar coordinates like this. So rho is the radius and phi is the angular part. So we take this Fourier transform and then integrate out the nth for a component in this way. Okay, that's going to be our beta. And if we now evaluate beta n at a very, very specific radius, then we actually retrieve our coefficients alpha. Okay, again, lambda nk, that's the kth root of the nth Bessel function. So it's it's a constant that's known. You can pre-compute it if you want. But the point is, if you take this helper function, evaluate it at a special radius, and you get what you want. And the proof of this is an explicit calculation. So we compute the Fourier transform f, So we want to compute the Fourier transform of these basis functions. And we can do that explicitly. So then, when we write down the definition of the Fourier transform, we evaluate everything in polar coordinates. So the complex exponential in polar coordinates. And then we use this expansion here, the Jacobi-Anker expansion. You just plug that in, and you plug in this definition of beta, and then use some orthogonality properties of the Bessel functions, and this just falls out. Okay, so it's not long calculations, maybe half a page to a page, but I don't think I'll say too much more about it. Okay. So this is this analytical identity that we have. And now we want to try to capture this in an algorithm and do this discretely. So what do? Well, we can take the continuous identity and just plug in the natural discrete counterparts and see what happens. So what are we doing here? Well, here we have a continuous Fourier transform. So we'll just replace that by a DFT. That's the first step. So we want to compute the DFT at all the points that we care about. And which points are those? Well, the radii that we care about are all these lambdas. Okay, so we compute the DFT at all the lambdas. And then how about the angular parts? Well, we need enough points that we can compute this integral by quadrature. So we just, for instance, we can take them uniformly just on the circle. Okay, so then we have this quantity, and all we have to do now is compute this integral by quadrature. And since this is just, Fourier transform, we can just do FFT here as well. So we'll end up with not the continuous beta, but some kind of discrete counterpart to these betas. And we're hoping that that is close to the coefficients that we care about. Okay, so this is actually the entire basis for the algorithm, but there are two problems. So first of all, it's unfortunately not fast enough. I'll show later that we don't have to do too many FFTs, but we do, with this approach, have to use of the order of L squared FFTs of size L. So we end up with something that's L cubed log L. And that's too slow. We wanted L squared. So this is not good enough yet. And secondly, it's not completely clear exactly what we're doing at this point. Because if I go back, this identity holds for continuous Fourier transforms. So it's not super clear exactly what we end up with when we start replacing the continuous thing by the discrete things. Remember, we wanted to end up with approximations of these matrices B and B star. So it's not super clear at this point that that's actually what we end up getting. But luckily, both of these questions can be answered. So to this first part, turns out we can use fewer points for our FFTs and do fewer FFTs, and instead do some kind of interpolation of this helper function. Okay, that's going to speed it up enough that it will be L squared log L. And for the second part, we're lucky. It turns out that the quantity that we get with this discrete operations is actually exactly B star F. So yeah, we're going to keep talking about this for a little bit, but I do want to say that this algorithm, it will approximate B star F, and then if we want B, we're just going to do the adjoint of all these operations that we do, and we end up with an approximation to B as well. So that's no problem. All right. With this in mind, we can actually write down the full algorithm. And just for good measure, I'm going to write it down twice, one here in formulas, and then once here with images, just illustrating what's going on. And it might be clearer just trying to look at the images and not caring too much about the formulas. Okay, so what do? Well, we take this image that we want to expand, and it's in real space on a Cartesian grid, and we do a non-uniform FFT onto a grid in Fourier space. So this grid has uniform points in the angular direction, but Chebyshev nodes in the radial direction, like this. Okay, so you might, if you look closely, you might see that these look like Chebyshev points. that's the first step. That's what I try to write out here. And the next step is that for each radial shell, what we do is we take an angular FFT here. So one at the outer radius, one at the next radius, and so on. And we end up with a quantity defined for each of these Chebyshev grid points. Okay, so that's what I call beta here. So that's not quite the continuous beta that we had before, but it's the discrete counterpart. And if you, I go back, sorry, what we want is beta evaluated not at Chebyshev points, but we want them evaluated at these special points lambda and k. So the last step of the algorithm goes from beta evaluated at these points to beta evaluated at the lambdas that we care about. And then this beta will be some kind of approximation to the continuous beta, which is hopefully what we're looking for. Okay, and that's the entire algorithm. They're just 3 steps. And we'll keep talking about it on the next couple of slides. But the main points here turns out to be, okay, there are 2 points. So one is that this actually computes what we want, so B star applied to the image. And the second point is that if we end up not having to use too many grid points here in this intermediate grid, then it's going to be fast enough. Okay, so it turns out if we prove that in this product grid, we only need order L angular nodes and order L radial nodes, then we're going to end up with a total complexity L squared log. Okay. So I want to expand a little bit on that statement. So I want to just give some ingredients on why we can get away with order L nodes in both these directions. So I have 2 slides here. They're very short, so I think we can go through them. So this slide talks about the number of angular nodes. And it turns out that it'll be enough to choose them of the order of max L, that's the image side length. And then we have some accuracy parameter here. So if we choose S to be of this order, then this inequality is going to be true. Okay, so some quantity is going to be less than gamma. Okay, we can think of gamma as being small. So this quantity, whatever it is going to be small. So why do we care about this quantity? Well, if we stare at this long enough, we're going to see that the output of the second step of the algorithm is related to this. So if we take this thing, multiply it by the image value at pixel j, and just sum it up, that's roughly, not quite, but it's roughly going to be the output of step 2. Okay. And how about this one? Well, this is related to entries of this matrix, because this almost looks like the complex conjugate of the basis function, right? So if we here had, instead of rho k, had this lambda nk, then this would exactly be the basis element, so psi nk evaluated at rj and theta j with the conjugate. Okay. So this is what we get as the output of step 2, and this is what we want. So it's probably a good idea that these are small. Okay, so the proof of this is not long. If you look at this is a Riemann sum of this integrand here. So it's a Riemann sum over phi. So instead of looking at the Riemann sum, you can look at the analytical integral of that, and that turns out to be exactly this. Okay, so to bound this, we just have to do some normal quadrature bounds with the trapezoidal rule. So all we have to do is bound the derivative of this guy, and that's possible to do. Okay. I want to say a few words just about the philosophy here. So a couple slides ago, I mentioned that we did not want to do, we did not want to care about the smoothness of the underlying image generating function or anything like that. And we've pulled that off because all we have to prove are derivative bounds on this helper function. Okay, the image doesn't come in here, the property of the image doesn't matter. So all we care about is this very special helper function. So this is all we have to prove for the angular nodes. And we can do something similar for the radial nodes. So we have, again, of the order of max, image side length, and accuracy parameter. Then something good is going to happen. Okay, so it turns out we're going to get this bound here. So we take an interpolating polynomial of this function here from the Chebyshev nodes to any point, any radius rho. And then the interpolated thing minus something that I'll show that we care about in a second is going to be small. So again, why is this important? Well, if we take this thing, multiply it by fj and sum it up over j, that's roughly what we get at the end of the last step of the algorithm. And how about this thing? Well, if we evaluate this at rho equals to nk, sorry, lambda nk, then this is exactly an entry of b star. Okay, so this is exactly what we wanted to approximate, and this is roughly what we get at the algorithm, and this is going to be small, meaning that the algorithm approximates the quantity that we care about. Okay. And the proof of this, again, it's not easy. Sorry, it's not hard. It is easy, because all we have to do is we do interpolation bounds on this very specific helper function here. We don't have to care about the properties of the image again. Okay, so there are some more steps in the proof, but I think I will leave the proof of the algorithm here. There are some cross terms that we have to care about. So this, in fact, is not equal. It's approximately equal. So there's some more terms. And it turns out that you have to care a little bit about pointwise L1 norms of the interpolating polynomials and some other things. But it's not too bad, and it's possible to pull it all together. Okay, so let me just go back to the overview of this algorithm again. So what I tried to motivate now was why this grid doesn't have to be too large. Okay, order L radial nodes, order L angular nodes. And once we've done that, it turns out to all work. So we end up with complexity of the order of L squared log L, and it approximates this operator B star. So I think that's actually all I wanted to say about the algorithm itself. I do have some computational results on the next slide, unless there are any questions. No, okay. Then I just have some benchmarking results here. So I want to talk about the accuracy and the timing. And we'll start with accuracy. So I have a table here that's going to show the relative residual of applying B, that's here, and applying B star, that's here, as a function of two parameters. So there's going to be the image size, the side length, and a precision that the user can set. Okay, and I've defined residuals here. So the error alpha, that's the residual applying B. So we get these bases. Sorry, other way around. This is the error of applying B star. So we get the basis coefficients alpha from the image. Okay, so there's going to be the fast method of doing it using the algorithm I just talked about. And then there's the dense one. So again, what's the dense one? Well, that's when we actually compute this entire matrix B, and then we do a mathematic product, and we end up with what we want. And you might notice now that this is L2 to L2. Okay, before in the theoretical statement, there was L infinity to L1, but now just to make it a little stronger, we looked at L2 to L2. Okay, and then same for applying B here as well. So that takes basis coefficients and evaluates them onto a grid. And you can see that we get good results. So the relative residual for both of them should be less than the precision epsilon here. Okay, and that's the case everywhere, except for when we get down here to machine precision, because there's some round off happening. But basically, we can tolerate this precision, and we get an accurate transform. Now, the next question is, it's accurate, but is it fast? And it turns out to be the case. So I'm going to show two figures. One is about pre-computation, and one is about actually applying the algorithm itself. And we're not using too big a computer here. So it's a nice desktop computer, but nothing crazy. In this experiment, it has 24 gigabyte of memory. It used to have 32, but we spilled coffee on it halfway through. So one memory stick got fried, so we ended up with 24. Okay. So we have two figures, and we'll talk about the pre-computation first. So for the dense method, that's in red, ours is going to be in black. For the dense method, the pre-computation consists of actually computing this big matrix B. Okay, so it's going to be an L squared by L squared matrix, and we generate that once, and then we can apply the method in this figure here. And we actually ran out of memory, so we can do, for that dense method, we can only do up to roughly L160, maybe a little higher. But that is not the case for our algorithm here. So for us, we pre-compute some data structures. So nothing as big as that matrix, but just some helper structures that we'll use when we actually apply B. Okay, and then how about actually applying it? So again, we can't go over L roughly 160 because for the dense method, because it ran out of memory, so we couldn't even generate a matrix. So how can we apply it? We can't. But ours works, and we get roughly 2 orders of magnitude speed up compared to the previous, or the dense way of doing it. Okay, just for fun, we looked at numbers, and if we did correctly, if we wanted to do this dense method and generate this entire matrix for an 512 by 512 image, we would need roughly 640 gigs of memory. So 512 by 512, that's not a terribly big image, and already there, the memory comes off. Okay, that's going to be it about this, how we designed this algorithm. And now I want to talk a little bit about this application that I hinted at before. But if there are any questions, now would probably be a good time for it. Okay, good. Then we'll jump into the application. So this has something to do with covariance estimation for cryo-EM images. So I'm going to have to explain what cryo-EM is, and then we'll talk about the covariance estimation part. And this is joined with, again, with Nick Marshall and Amit Singer, but also with Yunpeng Shi, who's now at UC Davis. Okay, so we'll talk about cryo-EM first. So what is it? It's a computational microscopy tool that biologists use when they need to image molecules like this. So this is a particularly nasty molecule, it's COVID. And when biologists want to design drugs and vaccines, they actually have to, get a 3D model of this molecule so they can look at it and see what they have to do to get rid of it. And you can do that with cryo-EM. And the first step turns out to be doing something physical with a microscope, and then there's going to be some math. So for the physical part, what they do is they take a sample containing the molecules they want to image. So it could be a nose swab or a saliva sample or something. But you take that and then you freeze it. So you end up with something like this. So this is a frozen substrate that contains many copies of this molecule. And then you put it into an electron beam and you get projection images that look like this. So each of these little blobs, they are projection images of the same molecule, but with different orientations. So when you freeze this thing, the molecules, they can turn, they can rotate. So you end up getting projection images of randomly rotated copies of this molecule. But you get many of these images. And clean images look something like this. But in actual data sets, there's a lot of noise, so it looks a little bit more like this. So this is to the point where it's so noisy you can barely see that there are particles in it. Okay, so then the mathematical problem becomes of taking these kinds of images and doing some magic and ending up with a 3D structure like this. So that's what we're going to talk a little bit about now and tie it into using this basis that we discussed before. So the image formation model is something I wrote out here. So what happens is you take your molecule, you rotate it randomly by this rotation r, and then you project it with this integral. Okay? But then there are two sources of noise. So this one here is just additive noise in each pixel. And this one is something that's a little bit more interesting. So it turns out that there's a physical process in the microscope that causes aberrations in the image. So you end up getting convolution with this function that's called a point spread function that basically makes everything a little bit more blobby. And I have one more slide just discussing this a little bit more. So what does it do? Well, the point spread function, like I said, it's a physical phenomenon that you can't really get rid of experimentally. It's going to be there, and you have to try to take that into account mathematically. And it's problematic because it ends up destroying information. So this is an example of the point spread function in real space, but basically it's a radial function that oscillates around 0. As it turns out, in Fourier space, it also oscillates around 0. So it's going to have parts where it is equal to 0, which means that when we do this convolution, we're convolving with something that's 0 in Fourier space. So we get multiplication with something that's 0, and we end up destroying information here. Okay, so that's a problem. And I tried to illustrate it here. So this is a point spread function. That's a clean projection image. And this is the result of convolving this with that. And you can see that it's a little bit blurry. The dark parts here are zeroed out, and you lose a lot of information. Okay. So that's it for physics. So what do we actually want to do here? Well, what we want to do is estimate the covariance matrix of the clean projection images F. So I've written out the definition here. So expectation here, it's over these unknown random rotations. So it's covariance estimation under group actions. So how can we do that? Well, the problem is that we don't get access to samples of F. We only get access to samples of G, where there's noise and there's this point spread function jumping around. So we have to try to take that into account. But why do we care about this? Well, this has to do with the images I showed before. So first of all, we can use this to denoise these very noisy images. We can use them to do PCA. So often in this context, we have data sets that contain hundreds of thousands of images, sometimes millions of images. So you might want to summarize them into PCA or using PCA. And there are some other parts as well that people care about in this cryo-EM literature. And if anyone cares about covariance estimation under rotations, this might be interesting to you as well. Okay, so I have a disclaimer slide here just to keep the presentation honest. It's not super important, so if you're not interested, you can go ahead and zone out for a minute. But there are 3 assumptions. So we will assume that this point spread function is radial. That's typically the case, but if it's not exactly radial, you can use this as a first order model and then try to correct it. And secondly, we assume something about the distribution of these random rotations. And I've tried to illustrate that here. So in general, these random rotations are not going to be equally likely. Okay, so I have one rotation here. So this rotates, so the z-axis of this coiled molecule ends up at the top, and then it's projected. The second projection makes it so that the y-axis looks upwards and then it's projected. But it's the same molecule, just from different directions. And this does not have to be equally likely to occur in our data set as this. Okay, they can be completely different. But what's typically the case in these data sets is that this thing here, and anything you can get by just rotating this image around its axis, like this, these should be equal likely. Okay, and in the same way, this should be equal likely to that. And that just happens to be the case physically. Okay, and then there's one more technical condition that we don't have to. Okay, so those are the assumptions, and what do we do with them? Well, turns out that the key step is to expand all these projection images that we get into a suitable basis. And you might guess by now that that basis is going to be the Fourier-Bessel basis. And that's just because of these properties that we mentioned before. So we have this fast basis expansion now from the previous results I mentioned. So that means that we can transform all of these hundreds of thousands of images into and out of the spaces quickly, which is important. But then we also have these structural properties that this convolution with the radial function, so the point spread function, that has a very simple structure. So it becomes a diagonal operator. And we can also rotate things very easily once we've expanded. And this turns out to be exactly what we need for this covariance estimation. Okay, so what I want to do now is talk about points 2 and 3 briefly. So we already talked about 1, that was the first half, but why are 2 and 3 true? Okay, so this is the same table as before. I'm just, again, showing that the Fourier-Bessel basis has all these properties. So green, 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 green. And some other nice bases might not have all the greens. They have some red angry crosses. I think there's a question. Let me check. Okay, sorry. Okay, so we'll talk about points 2 and 3 and why they're true. So they turn out to be faster to talk about than the fast code. So this is going to be just one slide about why the convolution with radial functions becomes a diagonal operator. So it's a small observation. It's maybe 2 paragraphs to prove, but we can go through it. So if we have a continuous function that's expanded in this basis with coefficients alpha, and we have a radial function h here, then what does the expansion of h convolve with f look like? So here, P is a projection just onto the same set of basis coefficients as before. Okay, so just to see what happens to these coefficients here. So it turns out that you'll take the same expansion, but just multiply each coefficient alpha by a function here, which it's not obvious why this should be the case, but it turns out to be true that you should take the Fourier transform of h and just evaluate them at these magical points lambda and k. So again, that's the kth root of the nth Bessel function. And then this is true. Okay, so I don't want to actually prove it, but if you believe it, you can see that this means that this radial convolution becomes a diagonal operation because we just take each basis function and multiply it by some number here. Okay. How about the last one? So that one is even quicker to talk about. So let's see what happens when we try to rotate these things. So if you rotate each basis function, we just add an angle to the argument. And where does that pop out? It pops out into the complex exponential. So we can just take this phase factor and move it in front. Okay, so that means that if we have an expansion of an image into this basis, we just take each basis coefficient and multiply them by a complex phase. And that's it. Okay, so it's also a diagonal operator. And that's actually all the ingredients that we need. So let's go over the covariance estimation algorithm. So it's containing these 2 equations here. So we'll just get there in a second. And the first thing we do is we take the image formation model that we had in real space. This is the same as before. And just translate it into Fourier-Bessel space. Okay, so here G, H, F, and E, they are vectors of coefficients of, capital G is the expansion of the lowercase g into the Fourier-Bessel basis. Same for F and same for E. And H is the vector, if I go back, consisting of these coefficients here, the H hat. And now this product here is element-wise product, because again, the convolution with the radial function becomes a diagonal operator. So we have a statistical model that looks like this. So it's very structured, very simple. And then we care about the covariance and means generated from this model. And this turns out to be a simple enough structure that there are actually closed form solutions for the means and the covariance that we can write down. And not only closed form, they're actually also very fast to evaluate. And I'll talk about that in 2 slides. But I have just one more bonus slide here, because it turns out you can speed this up even more. Because in this special Fourier-Bessel basis, the covariance matrix turns out to be block diagonal. Okay, so typically, if you want to estimate a covariance matrix, it would look like this. It would be L squared by L squared. But we only need to care about the non-zero parts, which are here in green. Everything else is zero. Okay, so we have much fewer coefficients there. And I have a short proof of this, just in case anyone is interested in this for other rotations. Okay. So this actually falls out from the assumption that we had about in-plane, that in-plane rotations should be equally likely, because that means that if we take the covariance matrix and we rotate it, we'll get the same thing. So in particular, we can integrate it out over all different rotations, and we'll get this equality here. So with this, we can just plug in the expression up here, and we get this. And now we can use the fact I mentioned about rotating these basis functions. We just get phase factors. So we end up with one phase factor here, and then one negative phase factor from here, and we get this integral. So this integral is nice because it's non-zero if and only if n is equal to n prime, right? So we get a little delta function here, and we can stop here. So we've shown that this should be equal to that. So that can be the case only if and only if the coefficients are non-zero only when n is equal to n prime, meaning that if you order things in the right way, then things will be blocked diagonally. Okay, so it's a much smaller covariance matrix. It only has a sort of L cubed coefficients that we need to estimate. Okay, those are all the ingredients. We can now plug things into that closed form solution that we had, and we can evaluate things. And have just one application here showing how much faster this is compared to old literature. So again, our method now is going to be in red. The old one is going to be in black. And what we're doing is we're estimating covariance matrices of these data sets that have hundreds of thousands of images. And then we are denoising them using a Wiener filter here. Okay, so once you have the covariance matrix, there are many things you can do, and we choose the Wiener filter just to denoise. And sorry, this data set only had 10,000 images, but I'll show some larger ones in a second. Okay, so I'm showing results in terms of the image side length and another physical parameter that we don't have to care about, but that's the x-axis here. Okay, so you'll see that our method is faster, and it's up to 3 orders of magnitude faster. That's speed, but what does it look like? So now I just want to return to these denoising things that I showed before. So we have clean projections that look like this. Then we get noisy things that look more like this, and we want to denoise them. So the next column is using this old method I talked about, and this is our new method. And you see that both of them do a pretty good job. Looks like they're doing roughly the same job, but ours is much faster. And just one more data set. So this one has 100,000 images and has more noise. So this, again, if you look at it, it's so noisy you can maybe see that there's something in there, but not quite. So when you denoise it, the old method looks like this, and ours looks like that. And again, there are some artifacts going on, but at least it's fairly close to this, and it's fast. And then this, just to tie it all together, this is the same image I showed before. So again, clean, noisy, and denoised. And for this one, we couldn't run the old method. It ran out of memory, but ours works just fine. Okay, I think I'll stop that and just mention 2 takeaways. So there were 2 parts of the talk. We talked about how to expand images into this particular basis, and we could do it fast and accurately. And then we used it to do a rotation invariant covariance estimation. And in case anyone is interested in chatting more about that, I'd be happy to. And we have 2 references here. Thank you.
All right, let's thank the speaker by clicking buttons. And we'll stop the recording here.